Welcome to Mathematical Finance. Today, we are diving into one of the most famous and revolutionary equations in all of economics, the Black-Scholes formula. Imagine you want to buy a house next year, but you are worried the price will skyrocket before you can save enough money. To protect yourself, you pay a builder a small fee today for a special contract locking in the price. That is exactly what an option is in finance. We will learn how to calculate the exact fair price for that kind of contract. Now that we understand the basic idea of locking in the price, let us define what we are actually pricing. In finance, this special contract is called an option. It gives you the right, but importantly, not the obligation to buy or sell an asset at a locked-in price. The fee you pay for this right is called the option premium. The Black-Scholes formula specifically prices what we call a European-style option. This is a strict type of contract that can only be used or exercised on its exact expiration date, not a single day earlier. If the market is highly unpredictable, the person selling you this contract takes on more risk and will naturally charge you a higher premium. Before we look at the math, we need to know what information the formula requires. To figure out the fair price of an option, the Black-Scholes model looks at exactly 5 key ingredients. First, the current price of the stock today. Second, the strike price, which is the locked-in target price you agree upon. Third, the time left until the contract expires. Fourth, the risk-free interest rate, which represents the guaranteed return you could get from a safe government bond. And finally, the stock's volatility. Volatility is a crucial measure of how wildly and rapidly the stock's price swings up and down over time. By combining these 5 ingredients, the formula acts as a pricing machine, spitting out a fair price tag. Now that we know the ingredients, let us look at the mathematical recipe for a European call option. A call option gives you the right to buy the underlying stock. The formula balances the expected benefit of buying the stock outright against the cost of paying the strike price later. Here, C is the current fair price of the call option, S0 is the current stock price, and K is the strike price. The term e to the power of negative r times t is a mathematical discount factor. It shrinks the future strike price down to its present value today, using the risk-free interest rate r and the time to expiration t. If the stock price increases, the call option becomes more valuable. If time runs out, the value drops. This formula we just saw leads us to an important question. What are those n functions? They represent probabilities based on a standard normal distribution or bell curve. They tell us the likelihood that the option will actually be profitable. To find them, we first calculate 2 intermediate factors, d1 and d2. We calculate d1 using the natural logarithm of the ratio between the current stock price and the strike price, adjusted for time, interest, and volatility, represented by the Greek letter sigma. Once we have d1, finding d2 is much simpler. We just shift d1 downward by the total volatility over the lifespan of the option. As volatility increases, the spread of possible future stock prices widens, which ultimately increases the value of the option. Before we move on, let us see this with a concrete example. Imagine a stock is currently trading at 50. You want to buy a call option with a strike price of 50 that expires in exactly 6 months, which is 0.5 years. The risk-free interest rate is 5% and the volatility is 20%. We need to find the fair price. First, we substitute our known values into the formula for D1. Notice that the ratio of the stock price to the strike price is exactly 1 and the natural logarithm of 1 is exactly 0. This makes perfect intuitive sense because the option is currently sitting exactly at the target price, meaning no growth is needed to reach it. We then simplify the terms inside the parentheses. Continuing with our calculation, we multiply the simplified terms on the top and the bottom. Dividing the top by the bottom gives us our final value for D1, which is 0.2475. Now that we have successfully calculated D1, we can move on to the next piece of the puzzle. We need to find D2 by subtracting the total volatility over the time period from D1. We plug our newly found D1 value into the D2 formula, giving us 0.1061. Next, we look up these values in a standard normal distribution table to find the probabilities. For D1, the probability is approximately 0.5977, and for D2, the probability is approximately 0.5422. We are now ready for the final equation. Now we have all the individual pieces required for the main Black-Scholes equation. We substitute the stock price, the strike price, the discount factor, and our two newly found probability values into the formula. We calculate the first part of the equation, which represents the expected benefit of receiving the stock. Then, we evaluate the exponential term, which discounts the 50 strike price to its present value today. Finally, we multiply that discounted strike price by the second probability. Subtracting the discounted strike price cost from the expected stock benefit gives us the final answer. The fair price of this call option is approximately 3.445. This means you should pay exactly 3.445 today for the right to buy the stock at 50 in 6 months. Now that we have priced a call option, let us consider the opposite scenario. Suppose you want to protect yourself against the stock price falling. You would buy a European put option. A put option gives you the right to sell the stock at the strike price. We could use a massive, complex formula to find this price, but there is a brilliant shortcut called put-call parity. Put-call parity is a fundamental rule in finance stating that the price of a call option minus the price of a put option must equal the current stock price minus the discounted strike price. This relationship ensures that there are no risk-free arbitrage opportunities in the market. Let us look at the mathematical form of this brilliant shortcut. This equation is the famous put-call parity formula. The letter P represents the price of the put option, which is what we want to find. The other variables represent the call price C, the stock price S0, and the discounted strike price K times e to the negative RT. Because we already know the call option price from our previous example, we can just rearrange this rule to solve for the put option price. If the call price increases, the put price must also adjust to maintain this strict mathematical balance. Let us apply this formula to price a put option with the exact same terms as our previous example. We want to isolate P on one side of the equation to solve for it easily. By rearranging the algebra, we get a direct, simple formula for the put option price. We move the call price and stock price to the other side of the equal sign. Now we simply substitute the values we already know from our previous work. The call price is 3.445, the stock price is 50, the strike price is 50, the rate is 5%, and the time is 0.5 years. We plug all of these numbers directly into our rearranged equation. Continuing from our setup, notice the exponential term at the end of the formula. This is the exact same discounted strike price we calculated in the first example. We already know from our previous math that this evaluates to 48.765. We replace the complex exponential term with its calculated numerical value, making the equation look much less intimidating. Now we are left with basic arithmetic. Performing simple addition and subtraction from left to right gives us a final result of 2.21. This means the fair price to buy the right to sell the stock at 50 in 6 months is exactly 2.21. It is cheaper than the call option because the stock has unlimited room to grow upward but can only fall as far as 0. Now that we have calculated these prices, let us visualize how the formula behaves in the real world. The graph you are looking at beautifully illustrates the Black-Scholes call option price. The horizontal axis is the current stock price and the vertical axis is the call option price. The dashed hockey stick line shows what the option is worth at the exact moment it expires. 0 if the stock is below the strike price and a dollar for dollar profit if it is above. The smooth blue curve shows the Black-Scholes price before expiration. Notice how the blue curve is always higher than the dashed line? This extra gap represents the time value of the option, which is the premium you pay for the chance that the stock price might swing even higher before time runs out. We have covered a lot of ground today, so let us review the key takeaways. The Black-Scholes formula is a mathematical engine that calculates the fair price of an option by perfectly balancing time, volatility, and interest rates. We saw how to price a call option directly and how to use the elegant put-call parity rule to easily find the price of a put option. This formula completely revolutionized the financial world in 1973, transforming the chaotic nature of stock markets into a precise, manageable calculation. By mastering this formula, you have unlocked the fundamental language used by every major financial institution to measure and trade risk. Excellent work today.